Welcome back, everyone, to Rocks for Jocks. This podcast is for informational and entertainment purposes only. Today, I'm going to be talking about a question that I get frequently. Isn't the climate always changing? What part of climate change is human-caused? What part of climate change is just natural cycles in the Earth? Short answer is yes, the climate is always changing. But how much, which direction is it changing? That kind of thing is what we're going to jump into today. Earth goes through climate change in cycles, usually on very large scales of both temperature swings and large scales over how long those temperature swings take to happen. Humans have not been responsible for these changes in the past, mostly because these changes took place before humans were even around, hundreds of thousands of years ago, some cases millions or tens of millions of years ago. In contrast, some of the more recent climate change has been happening very quickly, over very short timescales. A lot of that climate change, as I'm going to discuss later, can be tied more directly to greenhouse gas emissions like carbon dioxide that we put into the atmosphere. And the reason that we can say those changes are tied to greenhouse gases is that those more recent temperature changes cannot be linked to the natural cycles that we've seen in the past. What are the historical patterns of temperature changes that we've seen in the past? What are historical patterns of climate change? Let's jump into things. We're going to go hit up the NASA website and learn all about it. Our climate is generally controlled by three different knobs, three different levers you can pull on. The first and most important are going to be forcings. So those are going to be the initial drivers of climate. The other two levers that we're going to be talking about later are going to be feedback systems and tipping points. So forcings, I think, are the most important and the most interesting to learn about. So the biggest is going to be solar radiation, which just means sunlight. So we're all familiar with sunlight. Earth gets sunlight from the sun every day. But what's interesting about this is the amount of sunlight Earth gets on a yearly basis or a daily basis, a seasonal basis, actually changes a little bit over time. This is because of a couple of different reasons. The one that I'm most concerned with today, because it impacts long-term climate change, is going to be basically how the Earth moves around the sun on a yearly basis changes over time. The second forcing that we're going to talk about briefly is going to be greenhouse gas emissions. So these are going to be things that we're familiar with, like carbon dioxide and methane, both of which are produced in a bunch of different industrial and agricultural practices. Greenhouse gases, for the most part, act as like a little bit like a warming blanket. They fill up our atmosphere and help keep the Earth at a stable and warm temperature. The third category of forcings are going to be small airborne particles. So that's going to be things like dust and smoke and soot. That could be from natural processes like volcanoes or wildfires, or that could be from more human-caused processes like burning coal, for example. Broadly speaking, airborne particles have an effect of reflecting more sunlight than the Earth would otherwise get. So they actually have a little bit of a cooling effect, but they do tend to drop out of the air over long periods of time. So their effect gets limited by basically how long they've been in the atmosphere for. The second category I want to talk about here are going to be climate feedbacks. So those are going to be processes which either amplify or reduce the effect of a forcing. So if Earth has a constant amount of sunlight coming in, different feedback systems are going to amplify how much warming we get from that sunlight or try to tamp down how much warming we get. And those are going to be called positive and negative feedback cycles, respectively. The third category affecting climate change long term are going to be climate tipping points. Tipping points are going to be when Earth's climate shifts abruptly between periods of stable climates. For example, if ocean circulation system shuts down, or if a giant chunk of ice from Greenland or Antarctica falls into the ocean and melts. These are examples of tipping points that only happen when the Earth's temperature has changed by a drastic amount, and then a tipping point happens, and then the Earth's temperature continues changing by an even more drastic amount. If we're concerned about life existing on the planet at kind of like a stable, happy climate for everyone involved, we do want to think about tipping points in the long run. Okay, so I'm going to go back to the forcing section just for a couple more minutes here. Make sure I get the point across and kind of highlight something I think is interesting. So, as I mentioned earlier, solar radiation, sunlight, is going to be the most important one to ask questions about and get a good understanding of for long-term climate change, long-term shifts in the climate that happen naturally. The reason for this is that researchers at NASA and universities across the country and national labs across the country have done an awesome job of putting together impacts from all of the different factors that go into climate. And they do a really good job of kind of separating out the impacts of things like sunlight versus impacts from feedback systems and tipping points. It's not perfect. People are still working on more and more research for this every year, but the idea is that we're getting better and better over time, and we're starting to get a really clear picture of how some of these things work. So yeah, really excited to just kind of share that today and jump into a couple charts and figures. So this website here is climatedata.info. I'm gonna make sure I link all of the websites in the description to the episode. I want to highlight this figure 4 that I think is interesting. What we're looking at here is going to be a chart of solar radiation over time versus temperature on the y-axis. So we're looking at ice core from Antarctica, and we're able to kind of get a sense of how temperature changes in response to solar radiation over time. Broadly speaking, the temperature is this pink line. Solar radiation is the dark blue line. So as you hopefully can see, temperature mostly follows solar radiation. They kind of move up and down together over time. It is not a perfect system. As I mentioned, there are other forcings, feedback systems, and tipping points that also have a pretty big effect on climate change. I just wanted to highlight here how well the amount of solar radiation we get tracks temperature changes over time, and kind of emphasize that solar radiation as something that's been important when we look back several 100,000 years to see what have been the big drivers of climate before humans get involved. Moving on to the next article here, where I'm going to talk about some of the specifics of solar radiation, kind of what are some of the cycles specifically that drive that natural climate change over time. The first natural driver of climate change I really want to dig into here is something called eccentricity. The Earth revolves in a circular shape around the sun. That circular shape is not perfect. That circular shape changes every year by tiny, tiny amounts that are almost imperceptible. But we have really good scientists and researchers working on this stuff now. We can get really accurate measurements. We have satellites, we have telescopes, people all across the world working together to make sure we get the right kind of data. So here I have kind of a diagram where I'm going to show you how that orbit changes over time. Basically, it gets a little more smushed and extended for certain time periods, and then gets kind of starts to contract again towards the end of that cycle. This is going to be one of the actions that changes the amount of sunlight we get on a year-to-year basis. This cycle of the orbit extending and then contracting again takes 100,000 years. We're not going to notice this on a year-to-year or even lifetime basis. You're probably not going to get any clear records of changes. But if we look hundreds of thousands of years in the past, which we can do with things like ice cores and sediment samples from the bottom of the ocean, we can start to learn about this. The second change I want to talk about here with regards to how Earth receives sunlight and how that changes climate over long periods of time is going to be something called obliquity. So the Earth sits on a slight tilt relative to the way it orbits around the sun. It rotates on a tilted axis, and then at the same time, it moves around the whole sun. So this animation I'm pulling up on the screen right now is going to show us how the axis that we spin on actually changes a little bit over time from, I think it says here, 22.1 to 24.5 degrees. The reason that's important is because the amount of land exposed to sunlight changes drastically from 22 degrees to 24 degrees. Knowing where and when the Earth is at that different axial tilt has an impact on what we expect the climate to act like over long periods of time. Now that is going to be on a 41,000 year cycle. So similar to changes in eccentricity, this is not something that you're going to see in one lifetime or a couple of lifetimes. These are changes that we have to look at really long-term trends in the data to figure out exactly what's going on. The third type of way in which Earth's orbit around the sun changes a little bit over long periods of time and thus changes our climate is going to be something called axial precession. This is going to be when the axis that we spin around, not only is it going up and down over time, going from that 22 degrees to 24.5 degrees that I mentioned, it also kind of does this wobble over time. So I'm going to play this animation here. We can get maybe a better sense of things. And you can really see that axis wobbling over long periods, 26,000 year cycles. So why is this important? Well, similar to the axial tilt, we get the exact same amount of sunlight hitting the surface of the planet, but we get sunlight hitting different amounts of land versus water, which is going to be one of the big drivers of climate change. This is because land heats up faster than the ocean. There's a lot more land in the northern hemisphere than there is in the southern hemisphere. So anytime we get a redistribution of where sunlight is hitting Earth geographically, that means we're likely to get a change in surface temperature as well. As the NASA website explains, axial precession is going to make seasons more extreme in one hemisphere and less extreme in the other. Currently, we're looking at extreme seasonal variations in temperature in the southern hemisphere and slightly less extreme in the northern hemisphere. We're in about the middle of that cycle as well. There's a lot more detail if you want to jump into it. But to avoid getting bogged down in the details, I just want to highlight we have the 100,000 year cycle, eccentricity, the 41,000 year cycle is going to be the axial tilt, and the 26,000 year cycle of precession. Those are obviously going to have the biggest impact when they all overlap and you have all three cycles giving you hot temperatures at the same time. But there's also many cases when eccentricity is giving us the most amount of warming it can possibly give, but orbital tilt and precession are doing the opposite. Orbital tilt and precession might be out of sync. They don't all occur at the same time every single cycle. Okay, so moving on to the last article here. Another article from NASA says right at the top, 5-minute read. So if you ever want to jump into things, these articles from NASA, I think, do a great job summarizing what's going on and give us some really cool figures to take a look at. This part of the article here gives similar animations on those three cycles, kind of shows them all at the same time. And one thing I like about this animation is that you can see the cycles all happening out of sync. So sometimes one is having a warming impact while the other is having a cooling impact. So a couple things the article mentions that I thought was really important just to highlight before we close things out are going to be that Milankovitch cycles, the shortest one is on a 26,000 year cycle. So the recent Earth warming of the last 150 years cannot be due to these very long cycles. Even more importantly, in the last 150 years, solar radiation has actually decreased a little bit. So Milankovitch cycles are definitely not going to be to blame. It's definitely going to be really hard to say that natural climate change is responsible for warming of the last 150 years when NASA satellites show that solar radiation has actually gone down over that time period. So what does that mean for warming versus cooling? As you may be able to guess, if there were no human influences on climate, the decreased solar radiation would actually be causing a cooling effect on our Earth rather than a warming effect. Which means that warming of the last 150 years is going to be due to things like industry and agriculture. While they've certainly provided a lot of great things for humanity, making us more comfortable, giving us higher standards of living, have also contributed to a changing climate that we're going to need to deal with now. And as the article closes out, there is nothing cool about that. Great. Thanks a bunch for listening, everyone. Please subscribe to us on YouTube and Spotify and Apple Podcasts. I will talk to you all later. Take care.